Okay. So, couple of things before I start. So one, today's office hours I'm gonna actually hold on Monday instead of today. So the reason for that is since I'm gonna post your exam here like right after lecture. Anyway, it'll give you a little bit, I mean, obviously you're gonna have the weekend to work on the exam and have a look at it. But if you have any lingering questions about things, you can ask me. You can ask me on Monday. So since you technically have your second homework due tonight, if there's some lingering questions you wanted to ask about the second homework that you're going to ask today during office hours, you can just wait until Monday and ask me. You don't have to turn in the homework tonight. You can wait, and even if it shows up as late, it's not gonna matter. You're not gonna be penalized in any way. So you can also ask questions about the exam during Monday's office hours. Although since it's for the exam, I'll be slightly less helpful than I will be for any homework questions that you still have. So anyway, so that's that. I'll make an announcement after lecture, and I'll post your exam. So the exam it's mostly like you could think of it as kind of covering. So some of it is basically very similar to some of the homework, and some of it is basically some of the stuff I didn't necessarily get to in the homework. So anyway, so like I said, I'll post that right after lecture and make an announcement. So anyway, we ended the discussion last time. So before I move on to our topic, we ended the discussion last time talking about this fact. So we showed that this sum over all primes actually diverge, right? So if you consider this sum over all primes, this diverge. But if you consider a sum similar to the sum where you're actually summing over twin primes or pairs of twin primes, so it's not quite expressed like this, but it's like 1 over p plus 1 over p plus 2 wherever, and you're summing over primes such that p and p plus 2 are both prime. If that's the case, then this sum over pairs of twin primes like this actually converges. It converges, and I believe it's estimated to be something like 1.9 or something. And so the convergence of this sum, in contrast with the sum of 1 over p over all the primes diverging, tells you that there's, in some sense, much fewer twin primes than primes. Okay, which of course led me to state the twin prime conjecture, which is that there's infinitely many twin primes. So this hasn't been proven, but this is believed by many to be true. Has been proven, and to see, the main hang-up, basically, it's if you look at this this fact that this sum converges, there's definitely something different going on. And when you start trying to think about how to characterize twin primes, just the fact that you have so twin primes are what? They are primes that differ, right, by 2, right? So p and p plus 2 are prime. So it turns out that it is very hard to, in fact, it wasn't until relatively very recently that you could say something like there was infinitely many primes such that, say, or pairs of primes such that, p sub 1 and p sub 2 differed by some constant. Okay, it was only relatively recently that anything was able to be said about that, and even now the results about this are not complete at all. They're very there's a ton of work to be done. So yeah, twin prime conjecture very much still unsolved. Anyway, okay, so that's kind of the last bit of the chapter 5 stuff that I wanted to talk about. Okay. So, main topic today is modular arithmetic and congruence mod M. So, you may have already seen this previously, and there's various contexts in which this might show up. So, if you approach this from like your first course in proofs, it is probably one of the better examples of an equivalence relation. And to motivate this a little bit, you may have heard modular arithmetic called like clock arithmetic, because that's another good example of where something like this might come from. But one thing you might note is just for our original questions into divisibility, right? You just note that an even number is a number such that when you divide it by 2, the remainder is 0. That's one way to classify an even number. And similarly, an odd number is a number such that when you divide it by 2, the remainder is 1. Okay, so an even number is a number such that when you divide it by 2, the remainder is 0. That's just saying it's divisible by 2, right? Number is divisible by k if when you divide it by k, the remainder is 0. So even numbers is a number such that when you divide it by 2, the remainder is 0. And odd numbers is a number such that when you divide it by 2, the remainder is 1. Okay, this is equivalent to our usual definitions of even and odd. A couple things to note. Of course, a number is either even or odd, right? This is a completely exhaustive thing. Okay, and well, forgetting about the fact that you know this about even and odd numbers, forget about that for a second and just think about it in terms of remainder. Is when you divide by 2, is the fact that your possible remainders are 0 and 1, is that exhaustive? Well, yeah, because if you think about how many possible remainders are there once I divide by 2, 0 and 1. 2 is not possible as a remainder because if the remainder were 2, that would mean I could, there's another copy of 2 there. So if the remainder is 2, actually the remainder is 0. Similarly, if the remainder were 3, well, then I've just screwed up, right? There was another copy of 2 in there, and when I divide that 3 by 2, I would still have a remainder 1. Okay, so this completely partitions integers into two classes, even and odd, right? So this action of dividing by 2, and I'm using action here in a non-mathematical way. I'm just saying, so don't confuse this with something like a group action. I'm saying the action, it's just the process, I could say here, not just action. So the process of dividing by 2. So this process of dividing by 2 partitions the integers into two classes, even and odd. Okay. These two classes are disjoint and exhaustive in the sense that they completely fill out the space, right? So these two classes are disjoint and exhaustive. That is, if I have considered all of the classes, they cover every possible case that an integer could fall in. Okay. Okay. So if you want a more something like an approach that comes at it from, I should say, maybe an angle that offers more examples of, say, like clock arithmetic, which I'll mention here in a little bit. Then you can look at the treatment in the textbook, some of the examples in some of the paragraphs leading up to the things that I'm going to say. But I am going to approach it from the equivalence relation perspective. And we're actually going to see there's going to be a proposition that I state and prove in a little bit that literally says the thing that I'm talking about is an equivalence relation. Okay, so this thing that I said here, that my process of dividing by 2 partitions the set in question that I've defined this process on, the integers, into two classes. These are equivalence classes. Okay, so this process of saying that two numbers such that when you divide them by 2 they have the same remainder, saying that those two numbers are equivalent, that is itself an equivalence relation, and these two classes, okay, that are formed by this process are equivalence classes. And so it was, it was a fact about equivalence relations that kind of the most important thing about an equivalence relation was that it partitioned a set into equivalence classes, and it did this in a way such that everything in the set was in one of the equivalence classes and exactly one. So two equivalence classes were either the same or they were disjoint. Okay, and so that's exactly what happens here, right? There is no number that is both even and odd. It's split up like this. And of course, it turns out that it's not just dividing by 2 that does this. Dividing by 3 does it just as well. So here's another example. When I divide an integer by 3, the possible remainders are 0. That would mean that it's divisible by 3. And then there's 2 possibilities for when it's not divisible by 3. 1 and 2. Okay, so each case determines an equivalence class. So you might say, wait, what is the thing that you're even calling an equivalence relation to begin with? So that is the congruence that I'm going to define here in a second. So I know that I'm mentioning things that I haven't even defined what this relation is yet. But each case here determines an equivalence class. Later we'll see that this is called a congruence class. Okay, and if you want to list out some of these equivalence classes, so I'm going to go ahead and use the notation that you might have seen in a first proof course. For an equivalence class, you pick a representative. We're going to have a special name for the representatives we talk about. So like I said, right now in these examples, what you see might not make a ton of sense because I haven't actually built up the notation yet. But so there is the class determined by remainder 0. We write it with a bar over it typically. And so what are the integers that are in this class? Okay, well, these are the integers such that when I divide by 3, I get 0 as a remainder. And so going from minus infinity, when I divide minus 6 by 3, I get 0 as a remainder. When I divide minus 3 by 3, I get 0 as a remainder. 0 gives me 0 as a remainder. Then 3 and 6, 9 and 12, and so on. So all of those integers, when I divide by 3, I get 0 as a remainder. Okay. All right. What about the integers such that when I divide by 3, I get 1 as a remainder? Maybe it helps here to start with the things I know this is true for. So 1, right? And then what is the next number to the right such that when I divide by 3, I get 1 as a remainder? Well, 4, and then 7, and then 10, and 13, and so on. And so going back here, of course, now you see how it's easy to fill out this list. I'm just adding 3 or subtracting 3, right? Or multiples of 3 once I have this representative number. Okay, like I said, that we're going to have a special name for in the context of congruence mod m. So here this would be minus 2 instead, right? And minus 5, and so on. Okay, and then lastly, there's one more. There's what happens when you have 3, or sorry, when you divide by 3 and you have remainder 2. So again, it can be easier to just start out with 2 here, and we see that the next thing here is 5, and then 8, and then 11, and then 14, and so on. So here this is minus 1 and minus 4, and so on. Okay, so this is my list of numbers. Note that if I move on to the next in the list, 3 bar here, so that is, I'm going to center it here. I'm going to say here's 3, and then the next thing in my list is 6, and the next thing is 9, and the next thing is 12, and the next thing is 15, and so on, and then 0 and -3 and -6 and so on. But what do you notice? Well, in this list, I have listed out the numbers such that when I divide by 3, I get 3 as a remainder. Well, I know that just means that I've screwed up in this division, and actually this is remainder 0 case. So these numbers should be the same as the case when I divide by 3 and get remainder 0, and look, they are. Right? These numbers, I can find each of these numbers that have already previously been listed in this case. And notice that every single other number occurring here occurs in none of the other equivalence classes. So 0 bar is equal to 3 bar, and it turns out this is equal to 6 bar and 9 bar and -3 bar and 15 bar and 30 bar, right? All these are the same. Okay, just like 1 bar is equal to 4 bar is equal to anything else that shows up there. 7 bar, 13 bar. I don't know why I'm writing commas here. And 2 bar is equal to 5 bar is equal to 8 bar, and so on. What is it that I'm saying when I write this out? What I'm saying is that if I look at these equivalence classes as, you know, a list of numbers such that when I divide by 3, I get 3, well, that's the same as the class of when I divide by 3 and get 0 as a remainder. And that's the same as when I divide by 3 and get 6, 9, -3, 15, 30, any multiple of 3 as a remainder. Similarly, saying that I divide by 3 and get 1 as a remainder, that would be the same as saying I divide by 3 and get 4 as a remainder. It means that I can divide by 3 again, and that's the same as having a remainder of 1, right? Okay, and so as we see, these are the 3 classes I get. They are completely exhaustive for integers. Every integer falls in one of these classes, and there is no overlap. These are disjoint and exhaustive. So every single integer falls in one of them, and it only falls in one. They have no overlap at all, right? They are completely disjoint here. Okay, so what am I doing here when I write all this out? The idea intuitively, right? So the idea intuitively, this creates classes of equivalent objects. That's what these equivalence classes are. Okay. And so when equivalence relations were first explained to you, one of the canonical examples that's used instead of this modular arithmetic stuff, one of the canonical examples that's used is the notion of triangles. Okay, so when you study triangles, it is a natural question of talking about when two triangles are equal, right? When I look at two triangles, so here's one, and here's another. Okay, and let's pretend that all those lengths are the same and all those angles are the same. So I have a triangle ABC and a triangle like A prime, B prime, and C prime. Okay, and the question becomes, are these the same triangle, right? So question, Are these the same triangle? Okay. Well, if you are extremely restrictive with your notion of what the same means, you would say no, because this triangle's here and this triangle's over here, right? So the fact that they occupy different locations, right, simultaneously, here's this triangle, here's this triangle, the fact that I can point separately, here's one, here's another, means they're not the same, right? This one's over here and this one is over here, right? And even if you drew, like, say, the barycenter for this triangle in here, and both of these triangles had the same barycenter, it's just this one is, oriented differently, right? So you've taken it and you've spun it in some way. Even though they might have the same barycenter, so you might say they're, like, kind of in the same location. Even in that case, because the points that make up, right, this triangle, the collection of points that make up this drawing don't match up exactly with the collection of points that make up this triangle, they are not the same triangle. But you see that that is extremely restrictive. And if you restricted yourself to only considering triangles to be the same, if they fit that definition, it would be way too rigid. It would be pretty much impossible to say anything using diagrams of triangles, right? And so what you came up with was the notion of congruent triangles. All right, so you have the notion of congruent triangles. So what was the notion of a congruent triangle? Well, you had a lot of congruent. You had a like technical congruent like statement, right? It meant that two triangles are congruent if all of the corresponding parts were the same. Okay, so it's not that literally these were the same triangles matched up. So here's one, here's the other. It's that you had three side lengths here. If the corresponding three side lengths over here were equal, so if, say, AB and A prime B prime, those two lengths matched up, and all the other corresponding lengths matched up, and if all the corresponding angles matched up, then they were said to be congruent. But what that is really saying geometrically is that you can take this triangle or this triangle, and through what are called the isometries of the plane or rigid motions of the plane, you could take one of the triangles, apply one of these rigid motions, these isometries, so some combination of rotation, reflection, and translation, and you could, if you wanted to, take this triangle and line it up perfectly over that other triangle. So even if it didn't start like that, you could apply one of these isometries and do that. You could line them up so that after that process, after that action, they are the same triangle. Okay? Of course, that wasn't the only notion of triangles that belong to the same class in some sense. There was also the notion of similar triangles, which was an even looser notion than congruence, because for similar triangles, right, what mattered was scale. So it wasn't that the side lengths had to match up. In fact, in general, for similar triangles, that wasn't the case. It was that only the angles needed to match up. And what that meant was that you could scale one of the other triangles into the other. Okay, so our idea for numbers is to say that in some sense, integers in the same congruence class are equivalent. Okay? And at first, it may seem a little strange to say this. Okay? So at first, it may seem a little weird to say things like 7 is equivalent to 1 in some way when you're talking about division by 2. Or that 14 is equivalent to 0 when you're talking about division with respect to 2. But you'll see quickly why this is useful and how it makes sense to talk about those numbers being equivalent. Okay, so let me define the actual thing that I'm talking about so that I can start more efficiently giving examples. So definition. Okay, so two integers, a and b, are congruent mod m. Long form, you might say congruent modulo m. This came from the Latin saying modulo meaning with respect to the modulus. So I'll define that here in just a second. So two integers a and b are congruent mod m, written a is congruent to b mod m. Okay, if a minus b is a multiple of m. Okay. So this is to say that the remainder, when dividing by m, of a minus b is 0. Okay, that's another way of stating this. The integer m is called the modulus. The modulus, and is assumed to be positive. Nothing interesting can be gained by allowing negative modulus, and allowing 0 modulus we don't want to talk about, since m is the thing that you're dividing by in this process I described before, and we don't divide by 0, so that takes care of that. Also, mod 1 is not, nobody cares about mod 1 because that's a completely trivial case, and so the modulus practically is always going to be 2 or bigger. Okay, so what are some examples? Textbook lists a bunch. I had already listed a few here. Just go back looking at this thing. Well, these statements that I made in terms of equivalence classes, actually, these statements are the same as statements using this notation now. So for instance, 3 is congruent to 0 mod 3. That's this statement. 7 and 4 are both congruent to 1 mod 3. Let me put parentheses around this. Okay. Of course, 7 is congruent to 1 mod 2. Because it's odd. 14 is congruent to 0 mod 2 because it's even. Okay. Let's do some other examples. 19 is congruent to 7 mod 6. So think about that for a second. This is saying that when you're dividing by 6, 19 and 17 both share the same remainder. Well, when you divide 7 by 6, you have remainder 1. When you divide 19 by 6, you also have remainder 1. So yeah, that's true. Okay, minus 8 is congruent to 12 mod 5. Okay, 4 is congruent to 4 mod 11. So, quick question here. Is a number always congruent to itself mod anything, mod m? The answer is yes. This is the reflexive part of the statement that this definition defines an equivalence relation. So you might remember an equivalence relation is a relation that is reflexive, symmetric, and transitive. These are three properties that an equivalence relation had to satisfy. So this is the reflexive bit. I'll get to that in a little bit. Just one more. 6 is congruent to 16 mod 5. Right, so 6 and 16 both have remainder 1 mod 5. Okay, and so what we're writing out when we write this is we are saying in some way, right, modulo 3, 6, 5, 2, any of these integers, right, modulo m, okay, or with respect to the modulus m, with respect to division by m, these numbers are the same in some way. They are equivalent, I should say, rather than the same. Okay. Okay. So, this is, again, it is nice in the case that we talked about earlier with even. It naturally splits integers into even and odd. For division by 3, it naturally splits integers into 3 equivalence classes we don't really have names for. When the remainder is 0, we just call that being divisible by 3, right? Being a multiple of 3. When the remainder is 1 or 2, we don't have a name for those kind of numbers, but there's, if you have an integer and it's not a multiple of 3, then there's only 2 possibilities. When you divide by 3, you either have remainder 1 or remainder 2. So that's those other 2 remaining cases, right? And the same would be true if I chose anything. 4, 5, 7, 17. When you divide an integer by 17, the options for remainders are 0 through 16, right? And that would split the integers into 16 disjoint and exhaustive classes. Okay. And so that's that. So that's one thing to note. Here's another thing to note. We use base 10. So what does an integer mod 10 look like? So note, what is 1437 is congruent to what mod 10? Well, there's a lot of things I could say here, but what's something I can say immediately? Well, it's congruent to 7 mod 10. Why can I say that? Maybe I'll do another example. What about 35,320? Well, that's congruent to 0 mod 10. And let's do 78,453. That is congruent to 3 mod 10. Okay, well, what is the consideration of integer mod 10? What is that saying? It's just picking off the last digit. Right? It's just picking off the last digit of the number. Why does it do that? Right? Note that 1437 minus 7 is congruent to 0 mod 10, i.e. 1437 minus 7 is equal to 1430, and that is a multiple of 10. Another way of saying that, of course, 35,320 minus 0 is equal to 35,320, which is a multiple of 10. And lastly, 78,453 minus 3 is 78,450, and this is a multiple of 10. And so, looking at a number mod 10, if I take that number and subtract from it the number between 0 and 9, that is its last digit, right? It's the number in its last digit place. I'm always guaranteed to get a multiple of 10. And so I'm always guaranteed that any integer I pick, mod 10 is just going to be congruent to whatever its last digit is. Okay. Now note further that in general, there are infinitely many integers b once so a and m are fixed such that a is congruent to b mod m. Okay, so it's kind of confusingly worded because I left this here. I kind of spoke like Yoda for a second, did this kind of backwards. But say that you fix an integer a and an integer m, and then you want to ask yourself, how many integers b is a congruent to mod m? Well, infinitely many, right? These classes, these equivalence classes formed in this way are actually infinite in size. So 0, using our new terminology now, 0 is congruent to 3 mod 3, but it's also congruent to 6, 9, minus 3, 15, and 30 mod 3. Right? 1 is congruent to 4 mod 3, but it's also congruent to 7, 13, and the rest of those, right? So there are, really, I shouldn't just say in general, I should say it's guaranteed that there's no uniqueness here. Okay, so it's guaranteed, well, that's saying no uniqueness is a little bit silly here. It's guaranteed there's infinitely many integers once you fixed a and m such that a is congruent to b mod m. So these classes are necessarily infinite. Okay, so this is another example of where, thinking about this as clock arithmetic comes in. So for instance, the example is, say that it is 10 o'clock, right? It's 10 o'clock, okay, and then I ask you, what time is it 5 hours from now? Okay, so if it's 10 o'clock and 5 hours from now, what time is it? Well, you would, maybe when you're first being taught about time, you'd say, well, it's 15 o'clock, right? It's 10 plus 5. Okay, it's 10 plus 5. So you do 10 plus 5, and then you say, okay, that's 15 o'clock, fine. Now, if you're using like military time, there's no problem with that. But if you're using non-military time, if you're using just normal, 0 to 12 time, then what do you get, right? So from 1 to 12, you don't say 15 o'clock, you would say 3 o'clock. 5 hours from 10 a.m. is 3 p.m. Okay, so what did you really do there? Well, you still did 10 plus 5. You did 10 plus 5, that's 15. But then you said, well, what is that congruent to mod 12? Right? So we don't have, on our clock, we don't have any integers showing up bigger than 12, so everything gets modded by 12. And so 10 plus 5 is 15, mod 12, 15 is congruent to 3. Right? So 3 is congruent to 15 mod 12 and vice versa. 15 is congruent to 3 mod 12. And so 3 is the thing that I pick there. And that's why sometimes some of the first examples of this stuff you'll see is relates to clocks and adding time. Okay. So the thing is that, of course, there's as was said, right? There are ways in which congruence is very similar to equalities, and there's a reason why we use notation that looks like an equal sign in some way. I've just added an extra bar here. Okay, but there's some differences. So one of those differences is, just as I pointed out, there's infinitely many numbers that are congruent to, so there's infinitely many numbers congruent to a given number mod m. Okay. So that's certainly different. Whereas, if you're talking about how many integers are equal to 4, well, 1, right? There's one integer equal to 4, that's 4. Any other integer is not equal to 4. So that's different. Here's a proposition it's almost not even worth calling it a proposition because it is almost true by definition. It's literally just like a one sentence thing here. So A is congruent to B mod m if and only if A is equal to B plus Km for some integer K. And my proof is this is by definition of division, really. Okay. A minus B is a multiple of m. A minus B is a multiple of m. Okay, K is the thing that multiplies m there, so A minus B is equal to Km for some K, so A is B plus Km, right? That's the proof. That's barely even a proof. That's literally, it's almost true by definition. Okay. So as was mentioned, congruence mod m partitions the integers into disjoint and exhaustive classes called congruence classes mod m. These are called congruence classes. Okay. So the fact that I say these are disjoint, it means that given an integer, it is in exactly one of these classes, and none of the other classes overlap whatsoever. Okay. There's absolutely no overlap. Okay. So this is a little annoying, right? All these facts here tell us that it's a little annoying because, as was stated here, in general, there's infinitely many integers that are congruent to some given integer mod m. Okay, that's annoying for when you're wanting to do a computation, because when you're wanting to do a computation, obviously, you want to use a specific choice, right? So in this congruence class, which is going to contain infinitely many integers, I want to be able to single out one. And it turns out there's always a way I can do this. So when dealing with congruence classes, which are always infinite in size, we can always pick one preferred representative of that congruence class. So before I write this out, going back to my example to see how this choice is done, notice that to form these classes in notation, I chose some numbers here. 0, 1, and 2 were my chosen numbers, and those numbers represented their entire class. Okay. Well, how did I pick those numbers? Those numbers were just the remainder, the potential remainder numbers, right? And then everything else was used in reference to that. Okay, so there is a least non-negative residue. That's what those are called. Okay, so quick proposition that this can always be done. Again, this is essentially a definition, but it's listed as a proposition because technically you have to say one sentence to prove it. So if A is an integer and M is a positive integer, then there exists a unique integer r with r between 0 and m minus 1. What is this r going to be? It's in, our straightforward way of doing this, r is just going to be the choice of integer that is the remainder when you divide by m, right? It's now, of course, since technically you could say, oh, I divided, by 5 and I got remainder 17, right? What we mean here, of course, is it's remainder in the elementary school way, right? So if you told your elementary school teacher that you divided by 5 and your remainder was 17, you would have just been wrong, right? Even if you could have written it out using the division algorithm, you could have written it out using that expression, you would have just been called wrong, right? Your division would have been wrong. And so what we mean by remainder is this smallest remainder, right? It's the reasonable remainder, the actual remainder, whatever you want to call it. We're going to call it the least non-negative residue. So there exists a unique integer r with r between 0 and m minus 1, right? If r was equal to m, then that's the same as having remainder 0. Okay, so that a is congruent to r mod m. Okay, so this integer r is called the least non-negative residue. And some treatments of this will, instead of calling these congruence classes, we'll call these residue classes. So this is the least non-negative residue of A mod M. Okay. Again, as I mentioned before, this is not really this is not really a proof as much as it is literally just saying this is true by definition of division algorithm. So this is division algorithm. Okay. All right, this is just saying that I can choose my remainder specifically to be strictly less than m. Well, if it's a positive integer strictly less than m, the choices are from 0 to m minus 1 inclusive. Those are my choices for remainder. Okay, so quick example. If I go back through here, right? So let's pick here, right? So 1 is the least non-negative residue of 7 mod 2. Okay, here is 4 the least non-negative residue of 4 mod 11. The answer is no. What is a smaller non-negative residue mod 11 that works? 0, right? Is 16 a least non-negative residue for 6 mod 5? Of course not, right? 1 would be. So here, similarly, let's say 0 is the least non-negative residue of 14 mod 2. Here, so mod 5, 12 is certainly not the least non-negative residue of minus 8 mod 5. What would the least non-negative residue of minus 8 mod 5 be? Well, since minus 8 is congruent to 12 mod 5, to figure that out, I could just figure out what the least non-negative residue of 12 is, if the minus sign confuses you. And what's the least non-negative residue of 12? Well, the least non-negative residue of 12 is 2 mod 5. Okay, so 2 is the least non-negative residue of, say, 12 and minus 8 mod 5. Right? Another way of seeing this is I could add 5 to minus 8 twice. That gets me to 2. Okay. Oh, sorry. It's off screen a little bit. Okay. So that's how this goes. Okay. And so what this means is whenever you see the expression, and I keep forgetting my parentheses here, I will do that frequently. That's fine. In most cases, there's not going to be any issue there with the notation and being confused about that. So what that means is that if you come across an expression that has 7 mod 2, 14 mod 2, or minus 8 mod 5 showing up, instead you could just use 1, 0, or 2, respectively. Okay, for these numbers. Since these are all congruent, mod 2 and mod 5, you could use these instead, which are going to be, in general, the nicest numbers that you can use if you're dealing with congruences for those specific numbers. Okay, so now is the fact that I have been alluding to in my motivation for this all day. So fact. The relation A is related to B, or if you, so depending on how you've seen this before, A, R, B is another one, another way that you might have seen this. So whether tilde was used for relation or whether a capital R was used for relation in whatever course where you've seen this before. So the relation A, R, B, or A is related to B if and only if A is congruent to B mod M is an equivalence relation. Okay, so this is a quick reminder of your first course in set theory days. What's an equivalence relation? So it is, i.e., it is reflexive, symmetric, and transitive. It is all of those. So if you took 310 at UMD, then you probably had a lot of fun drawing pictures of relations and noticing from the picture whether it was reflexive, symmetric, transitive, whatever, coming up with examples of where it was reflexive but not symmetric or transitive, or where it was reflexive and symmetric but not transitive, where it was reflexive and transitive, not symmetric, and so on. These actually have nothing to do with one another. None of them imply the other, and there's an example of every possible combination of relation. But saying that something's an equivalence relation means that it's all three of these. Reflexive means that A is related to A. Symmetric means A related to B implies B related to A. And transitive means A related to B, B related to C implies A related to C. Right, that's the quick definition of those three terms. Okay. So the fact that this is an equivalence relation is summed up in the following proposition. So we have the following proposition. So mirroring these, if I'm claiming that this is an equivalence relation, then if A, B, C, and M are integers with M positive, then 1, A is congruent to A mod M. That's reflexivity, all right? That's the statement that it is reflexive. 2, if A is congruent to B mod M, then B is congruent to A mod M. That's symmetric. And transitive, if A is congruent to B mod M, and B is congruent to C mod M, then A is congruent to C mod M. Okay, so that's the statement of transitivity. Okay. So before I prove this really quickly, it's not going to take a whole lot of effort, but before I prove this really quickly, here's a refresher for what equivalence relations do for you, right? So I'd already said at the beginning of this course, equivalence relations, the point of them is when equality itself, right, using the equal sign itself is too restrictive, right? When I want to talk about the class of integers, right, that is equal to 5, right? Well, it turns out that's not a whole lot of integers. That's a single integer. There's one integer equal to 5. Okay, and so if I want to try to use some kind of classifying language about the class of integers equal to 5, I'm only saying something about one number. Okay, but similar to the issue for triangles, where if I used the notion of the same triangle that was very, very rigid, anything I want to say about triangles would only apply to that single triangle. If I come up with a notion of equality that is a little bit looser, right, a little bit more wiggly, then suddenly if I want to say something, or I find out that something applies to this entire equivalence class, then I'm saying something about a lot more numbers, okay, or a lot more objects here. So saying that a relation is an equivalence relation is saying that it behaves like the equal sign. Okay, so this is the statement. The fact that this is an equivalence relation says that congruence mod M behaves like the equal sign. This is important for us because in this course, a huge component of this course is solving equations in modular arithmetic. So it's solving equations in the mod M world. Okay, so solving equations in the mod M world, I have no idea how to do that a priori. I don't know anything about how that goes. So if this expression is behaving like the equal sign, that's good because I know already some basics of solving equations using the equal sign rather than the congruent sign. Okay, so what does the proof of this fact look like? So proof, part 1 is easy. A is equal to A plus 0 times M. Okay, i.e. A is congruent to A mod M. This is by the proposition from earlier. If you like, A minus A is equal to 0, which is 0 times M. So A minus A is a multiple of M. right? That's another way you could have said this. Okay. The second part, well, A congruent to B mod M implies that A is B plus Km for some K. But that means that B is A minus Km or A plus minus K times M. So B is congruent to A mod M. Okay, and again, if you're confused about why I'm able to say this, it's this property. Where did I put it? Here we go. This property I first wrote down, that A is congruent to B mod M if and only if A is B plus Km, right? So if I can write that, I'm done immediately. This is a nice form of saying that A minus B is a multiple of M. So here, if A minus B is a multiple of M, then B minus A is a multiple of M. You could have done it entirely in that language. 2, it's literally the same thing. 3, if A is congruent to B mod M, well, I have, so A congruent to B mod M implies A minus B is equal to, say, K sub 1 M, and B congruent to C mod M implies that B minus C is equal to, say, K sub 2 times M. Thus, if I look at A minus C, well, I can do some algebra trickery. This is A minus B plus B minus C. All right. So maybe I'll continue on. So proof continued. So A minus C is A minus B plus B minus C. So this is K sub 1 times M plus K sub 2 times M. So this is K sub 1 plus K sub 2 times M. So A minus C is a multiple of M. So A minus C is a multiple of M, which implies that A is congruent to C mod M. And that's it. Okay. Okay. So, congruence mod M is an equivalence relation, i.e., it behaves like the equal sign. Okay, i.e., we have hope of solving equations in, I should say equations here, in congruence mod M world. All right, so in whatever congruence mod M world means. All right, so an example. Say that I have like x minus 2 is equal to 3. Right? If I'm in equal world, so equality world here, what do? Oh, I add 2 to both sides, right? I add 2 to both sides. This implies I have x is equal to 5, and I'm done. I'm very happy. Okay, but algebraically, what is different about this versus x minus 2 is congruent to 3 mod 7, right? So what's the difference between this thing that I have here and this thing, right? So here's one example. Here's a second example. Well, algebraically, in this case, I knew there was a single integer, 2, that I could add to both the left and right side that would keep them equal. Right? There's a single choice. The second that I added plus 2, right? The second that I added 2 to the left-hand side, I had no option on what I had to add to the right-hand side to keep this equation holding, right? That's the rigidness of the equal sign. So because of the rigidness of the equal sign, the second I add 2 to one side, I have to add it to the other, or else I don't get an equality. Okay, and 2 is the only number there. But that's not the same here. That's not the case. So here I could add 2 to both sides, but what if I add 2 to this side and an integer that is congruent mod 7 to 2? So 9. Right? What if I do that? Well, let's try to do this in two different ways. So let's try to do it in my obvious way, where I add 2 to both sides. I add the same thing to both sides. And let's try to do it in this way. So if I'm doing it in this way, what do I get? I get that x is congruent to 5 mod 7. Okay. But here, because I'm using congruence, of course, I could have chosen any two numbers that were congruent to each other mod 7 to add. And in terms of keeping the equation balanced, I'm doing that, right? This congruence relation should still hold even if I've chosen a different thing. So let's check that that's actually the case. So here I get x minus 2, x plus 2, so that's x is congruent to 12 mod 7. Okay, so here x is congruent to 12 mod 7, here it's congruent to 5 mod 7, but wait. 12 is congruent to 5 mod 7. Oh. So it does work, right? And you can quickly convince yourself that it wouldn't have mattered what I would have chosen here. If I chose any other integer that was congruent mod 7 to 2, this would have been fine. Okay, in fact, I could have added 16 here and 9 here, and whatever I did after that, so long as I did something similar, it would have still worked out. I could still keep this congruence relation balanced in that way. Okay, so wrapping this up, this is to say that largely we'll say congruence algebra is similar to the basic algebra of solving equations with the equal sign. Okay. Of course there's differences, but there's a lot of similarities here, right? So yes, technically I'm allowed to add numbers that seem like they're different, but if they're congruent mod 7, then actually it all works out. So let's put this into a nice tidy proposition. So proposition that kind of solidifies this is the following. So assume that A, B, C, D, and M are integers with M positive. So A, B, C, D, M are integers, and M is greater than 0. Okay, if A is congruent to B mod M, and C is congruent to D mod M, then the following are true. So 1, A plus C is congruent to B plus D mod M. What is this operation? This is me adding two different equations, right? Equations here. Right, so this is me adding two congruence relations and getting that this congruence is preserved. I can also subtract, so A minus C is congruent to B minus D mod M. Okay. And lastly, I can multiply these things. So A times C is congruent to B times D mod M. Okay. So I don't have quite enough time to go into a proof of this fact. Well, I have a couple minutes. I think I might be able to get it done. So let's do a quick proof here. That way we don't have to do it on Monday. So since A is congruent to B mod M, and C is congruent to D mod M, A is equal to B plus K sub 1 M, and C is equal to D plus K sub 2 M for some integers, K sub 1, K sub 2. Right. All right. Note that A plus C is then equal to B plus K sub 1 M plus D plus K sub 1 or K sub 2 M, sorry, which is B plus D plus K sub 1 plus K sub 2 times M. Right? So if that's the case, well, this is congruent to B plus D mod M. A minus C, likewise, is B plus K sub 1 M minus D plus K sub 2 M. So I get B minus D plus K sub 1 minus K sub 2 M. But this is congruent to B minus D mod M. And of course, A times C is B plus K sub 1 M times D plus K sub 2 M. So multiplying this out, this is B times D, that's the terms that don't involve any of the K's, plus B K sub 2 M plus D times K sub 1 M plus K sub 1 K sub 2 times M squared. But there's an M in every one of these terms except the first. So this is equal to BD plus, I can factor an M out, so this is B K sub 1, or K sub 2, that's an integer, plus D K sub 1, that's an integer, plus K sub 1, K sub 2, M, that's also an integer, times M. So this is congruent to BD mod M. And that's it. Very, very straightforward. Okay. All of this early congruence stuff is really, really straightforward, but it's still important because even though this stuff is trivial in a sense, a huge ton of the understanding of what's going on here comes directly from this basic stuff. So anyway, that is it for now. What I'll say here is note division is curiously absent here. Division is curiously absent. So those of you that have had a proper algebra course may already be screaming at the computer screen as to why that is, and what that means, and what sort of restrictions it places on M if you want to have all of those operations and have them be nice. So we'll talk about that. I'll talk about that a little later. And specifically next time, first thing I'll do essentially is talk about why division is curiously absent in this list. Okay, why division is more tricky here. Okay. So anyway, that is all I wanted to say for today. So as I mentioned earlier, no office hours today. They're on Monday instead. If you have homework questions for homework 2, feel free to wait until Monday to ask them, so you don't have to turn in your homework until Monday. I know that's also when your exam is due, so you can. But you can take your time there. You're not going to be penalized for turning in your homework late. Anyway, okay, so that is all. I'll post an announcement with your exam here in like 10 minutes. So I will see you all on Monday.